Alright, so we are in the last section for chapter 8, and we're still talking about proportionalities. That's pretty much been the whole theme of chapter 8. The whole idea is using proportionalities. And proportionalities are setting up like ratios that are equivalent. So we could say A over B is equal to C over D. So this is what we've been dealing with over the last couple units. And now we're going to see how they apply to triangles in certain situations in triangles. So here are a couple theorems that we're going to go over to introduce some of these proportionalities. So this first theorem is the triangle. So the triangle proportionality theorem. Triangle proportionality theorem. So if we look at this this triangle right here, notice that these lines right here are parallel. So QS and TU are parallel lines that cut through the triangle QRS. So they cut through this triangle right here. Now, whenever this is a case, if we have two parallel lines and a triangle, then segments actually become proportional if the lines are parallel. So, so we could say that if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. Okay, so let's look over what this definition states. So if a line to one side, if a line parallel to one side of the triangle, so this would be this line right here. If it's parallel to one side of a triangle, then the other two sides, triangle intersects with the other two sides. So you can see that this line TU intersects with these sides right here, the other two sides of the triangle, and it's parallel to this side right here. So if this is the case, then it divides it proportionally, meaning that RT, so in this situation right here, RT and TQ, this proportion is equal to RU and US. So those are the equal proportions that it's saying. So we can set up a proportion just like this. Okay. So if TU, which is this line right here, is parallel to QS, then these proportions, then these sides are proportioned. So also note that the converse is true as well. Also note that the converse is true. And so what that means is if RT, so if we don't know that these lines are parallel, let's just say that we had two lines that are intersecting, or we had this line right here and this line intersects. If we find that RT over TQ is equal to RU divided by US, if we can prove that these ratios are equivalent, then that proves that this side right here and this intersecting line right here, that they are parallel. So that's what the converse states. Alright, so let's try it out in this example right here. So in the diagram QS, QS and UT are parallel lines. We have RS, that is 4 units, ST, that is 6 units long, and QU, which is 9 units long. What is the length? What is the length of QR? So we can set up, since we know that these lines are parallel, given here, then we can set up a proportional statement like this. So look at the leg. So we can say that the leg, so both sides of the parallel line, so we can say 4 to 6. We can set up a proportional statement of 4 to 6 is equal to RQ to 9. We can set up that sort of proportional statement. And if you want, you can say 4 to 6 is equal to x to 9. So we can say that this is our x side, so that's the length that we're looking for. So for me, I am going to multiply this by 9, multiply both sides by 9. Here they cancel. On the left side, that's 4 times by 9 divided by 6. So x is equal to 9 times by 4 divided by 6. 9 times by 4 is 36 divided by 6. So 6 is equal to RQ. Okay, so that's how you can set those up. So let's work on these ones right here. So these are parallel lines. You can see that this line is parallel to this line. So if that's the case, then this side right here divided by this side, the ratio of this side length right here is equivalent to the ratio here. So I could say that AB over 6 is equal to AE, which is 5, divided by 10. And so I can multiply both sides by 6. Here they cancel. So AB is equal to 5 times by 6 divided by 10. So it's equal to, I think that should be 30 over 10, so it's equal to 3. AB is equal to 3. Okay, so I want you guys to pause the video and try number 2. You should expect an answer of 14 over 9, just as a heads up. So you can check your work with that. Now let's come down here to example 2. This will be using the converse, okay? The converse of the theorem. So on the shoe rack shown, okay, BA is 33 centimeters. CB is 27 centimeters. CD is 44. And DE is 25. Explain why the shelf is not parallel with the floor. So we know that right here, so this is the shelf. I'll draw the shelf as an orange line here. So the shelf is right here. So we need to show why it's not parallel. And we can show that it's not parallel by proving that the proportions of the side lengths are not equal. So if I take this portion right here, so I can do 27 to 33. Set that equal to 44 over 25. Okay? And if you reduce these fractions, well, 27 and 33, this can reduce to 9/11ths. And I don't think that we can reduce this one right here, so 44 over 25. But here's the thing. This fraction right here, this ratio is less than 1. And I know that it's less than 1 because it's 9 divided by 11. It's a smaller number divided by a larger number, so it's less than 1. But this ratio right here, it's a larger number, 44, divided by a smaller number, 25. So this ratio is greater than 1. So these are not equal statements. So they are not proportional. Okay, so since we proved that they are not proportional by the converse theorem, so if these are not congruent, then the lines are not parallel. That's pretty much what we're saying here, because the converse says if you can prove that the segments, the ratios are equal, then that means that the lines are parallel. So here we prove that these proportions right here are not equal, therefore this line is not parallel to AE. So by the converse theorem. By the converse theorem, the shelf isn't parallel with the floor. And so by this, which is the converse theorem, it's not parallel with the floor. So in these exercises right here, we want to show whether or not, the same thing, we want to show whether or not AB and XY are parallel. So in this one, AB and XY, are they parallel? So let's try number 3. So let's set up our proportions. So we can say 3 to 4 equal to 4 to 5. Now, if you guys were to punch these into your calculator, you can do 3 divided by 4, right? So 3 divided by 4 we know is 0.75. Okay? If you do 4 divided by 5, you get 0.8. Now, these are obviously not equal, right? So they're not equal, so no, AB is not parallel with XY. Okay? Now I want you to do the same thing with example 4. Can you show that AB and XY are parallel? Show if they are or are not parallel. Okay, so moving right along, we're coming down here. So determine, so this one is using, this is a new theorem. So this right here is the triangle angle bisector theorem. So the triangle angle bisector theorem. Okay, so the triangle angle bisector theorem states that if any ray, or let's just say if a ray, now a ray, in this case we're talking about CD. So a ray is like you could say is a continuous line. So you see how it has the arrow pointing at the end? That's saying that it's a ray. So if a ray bisects an angle of a triangle, then it divides the opposite sides then it divides the opposite side into segments whose lengths are um, whose lengths are proportional to the lengths of the other two sides. So pause the video if you need a little bit more time to write that down, but I'm going to continue on with an explanation to kind of expound upon that. So if a ray bisects an angle, so you see when bisecting, if you can remember the definition of bisecting, means to cut in half into two equal parts. So this ray is bisecting angle C into two equal parts, meaning that this right here and this right here, these angles are equivalent because its angle C is being cut into half, and its halves are this this angle and this angle. So if that is the case, then the side opposite, then it divides the opposite side being this side right here. This is the side opposite to angle C. It divides it into segments whose lengths are proportional to the lengths of the other two sides. So basically saying that, so again, you can see in the statement right here, AD, so this right here, divided by BD, right here, is equal to CA divided by CB. These will be proportional. Okay, so that is basically what this is saying right here. So let's go ahead and use this on this next page right here, using the triangle angle bisector theorem. So in the diagram, angle QPR, so this angle right here, is congruent to RPS, so this angle right here. So basically what it's trying to tell us right here is that this segment right here bisects this angle, which tells us we can use the triangle angle bisector theorem. Okay? So use the given side lengths to find the lengths of RS. So we want to find the length of RS right here. Okay? So because PR is the angle bisector of QPRS, you can now apply the triangle angle bisector theorem. And so let's just say that RS is X. So that's what we're saying here. RS is equal to X. What that means is that RQ, this right here, is equal to 15 minus X. So if this segment right here is X, and if this distance right here is 15, then that means QR, if we take X right here, so 15 minus X, so if we subtract this distance right here, this is the distance X. If we subtract that from this distance right here, which is 15, then you'll be left with the distance of QR. So that's why we say RQ is equal to 15 minus X. RQ is equal to 15, subtract this distance right here. Okay? So what we can say from the triangle angle bisector theorem, we can say that RQ, the distance of RQ, divided by the distance of RS, is equal to the distance of PQ divided by the distance of PS. So the distance of RQ, as we know, is 15 minus X. The distance of RS is X. The distance from P to Q is 7, and the distance from P to S is 13. So we have set up this proportion, and we're trying to find the length of RS, and the length of RS is x. So basically, if we find the value of x, we can find the value of RS. So what I'm going to do is cross multiply. Now, cross multiply is a way of eliminating denominators. So let's eliminate our denominators. So I can multiply 13 by 15 minus x, and that is equal to 7x. So I can distribute this 13 to the 15, so 13 times by 15, I get 195 minus 13x equal to 7x. I can add 13x. So 13 plus 7 should be 20x, so I get 195 is equal to 20x divided by 20. So 195 divided by 20. So x should equal 9.75. So in that case, since x is rs, we could say rs is equal to 9.75. Okay. So let's come down here to these examples now and see how we can solve these right here. So find the value of the variable. So these are congruent angles, which means this line bisects the triangle, that triangle angle. So I can say that x to 5 is equal to 9 to 15. I can multiply both sides by 5. So here eliminates the 5 is equal to 9 times by 5, and 9 times by 5 is 45. So I get 45 over 15, and 45 divided by 15 is equal to 3, I believe. So x here would be equal to 3. So that was for 8. Now I want you guys to try this example 9 on your own as well. So just remember, I'll give you just a little tip. So this length right here is 14, and we want to find the length of B. Okay, that means this length right here, you have to take 14, so the total distance of this segment, and subtract B. So this segment right here is 14, subtract the length of B. So 14 subtract the length of B. That will give you your length right here. So you can use that. So you could use that to set up your ratio. Okay. You should get an answer, by the way, if you work this. You should expect an answer that B is equal to 8. So try it out and see if you can get that answer. But that should pretty much do it for us on proportionality theorems.